Molecular geometry. Whenever we mention of geometry here in chemistry, we are referring to the shape of the molecule. Every molecule has a shape to it, and it's very important that we figure out what is the shape of the molecule, because the shape of the molecule determines its function as well as its many physical properties as well. So therefore, for any given molecule, we want to be able to figure out what is the 3D shape or the geometry of a molecule. For an example, given a water molecule. Now, when we look at the little structure of a water molecule, it may look very flat. And in fact, little structure do not show the 3D shape of the molecule. It simply shows how the atoms are connected. So in this case, with water, it looks pure linear when we look at its little structure. But in the reality, then water, this molecule right here, the bond, these two OH bond right here are bent a little bit. So here in this case, it may look like the bond angle between this OH bond to the other OH bond is 180 degrees. But in reality, it's bent a little bit, and the bond angle is actually 104.5 degrees. And another example, if we were to have this molecule, this is called methanol. And this is the little structure of methanol. Overall, this molecule right here has a particular three-dimensional shape to it. And it turned out that the three-dimensional shape of a molecule is actually determined by however many central atoms that the molecule has. So in this case right here, with this molecule, there are two central atoms. So we have the carbon at the central atom, and the oxygen here, this oxygen right now is also the central atom as well. And it turned out that the overall shape of this molecule right here is determined by the geometry at these two central atoms right here. So how do we figure out what is the 3D shape of a molecule? Now, so the simplest method for us to learn and be able to figure out what is the shape of the molecule is by using something that we call the valence shell electron pair repulsion theory. And it's spelled like VSEPR, so therefore we call this VSEPR for short. And according to this VSEPR theory right here, then it is the amount of number of electron groups surrounding the central atom that dictate the geometry of the central atom. And overall, the geometry of all of the central atom then affect the 3D shape of the molecule. So here in our case right here with this example, water have one central atom. And right now surrounding water, there are 4 electron groups. So in this case, this bond right here is an electron group. This bond is another one. This lone pair is another electron group, and this lone pair is another electron groups. So water has oxygen at the central atom, and oxygen have 4 different electron groups surrounding it, and this electron group repel each other. So therefore, they have to be spaced out in such a way that they be furthest apart from each other to minimize the repulsion between the electrons. Because we know that electrons repel each other since they are all negatively charged. So in the case of methanol has 2 central atoms, and overall, this carbon is one central atom, and this oxygen is another central atom. So the geometry of the carbon is determined by the 4 electron group that it has surrounding it. And as for the oxygen, the geometry of the central oxygen is affected by the number of electron groups surrounding it. And here in this case, the oxygen have 1, 2, 3, 4. So there are 4 electron groups that the oxygen has. And again, they repel each other, so they have to spread out in as far apart from each other as possible, thus affecting the bond angle and the shape of the individual atom. And combining the geometry of all of the individual atoms add together, that becomes the shape of the molecule. So This to give you an example right here, and here I'm going to show you a very nice simulation to demonstrate electrons and molecular geometry. So there are two types of geometry that we have. One is something we call the molecular geometry, and the other one is the electron geometry. So here is a simulation that shows the electrons and the molecular geometry. So here in this case, I'm having a molecular model where a molecule it consists of one central atom, and that is the purple central atom here, and the two gray terminal atoms connected to it. So here in this case right here, because these atoms in here with electron in them, they repel each other, and because this group have two electron groups surrounding them, they repel each other. Thus, the distance that they have to spread out will then be 180 degrees from each other. Now, if I were to move this group down a little bit, then again you can see a push on the other group, and therefore it will push out again, and it will then stop whenever the two groups are as far apart from each other as possible, and that would then be 180 degrees. Now, so if we were to now add in another electron group, let's say if the central atom were to have 3 electron groups. So here in this case, I'm going to build another one in here. Let me replace that by another single bond. So here in this case, the central atom have 3 electrons group. And you can see as I move one of the group around, it push on the other. And if we were to allow the molecule to relax, we would then find that they will stop whenever the 3 groups are as far apart from each other as possible. So here in this case, the bond angle from this bond to the other bond here will be 120 degrees. And now if I were to now add in another group to the central atom, in this case 4 electron groups. So again, if we were to move one, it would then push on the other. And finally, when we allow the molecule to relax, so that they can be as far apart from each other, we would then find this is the kind of shape that the molecule would have. And the bond angle from each of this bond to another, it does not matter where it is, it would always be 109.5 degrees from each other. So that's how the number of electron groups surrounding the central atom that actually affect the geometry of the central atom. So let's see here, I'm going to delete one of this bond and now replacing one of that bond right there with a lone pair of electron. A lone pair of electron is also an electron group as well. So this lone pair is still repelling the other electron in this bond and the other atom. So thus you can see that there's not really that much differences in the bond angle from this bond to this bond right here if we were to have a lone pair here instead of a covalent bond. So if I were to now delete another and now add in another lone pair of electron, this, and assume now the central atom here is the oxygen, and now the white ball here are the hydrogen. This is indeed exactly the 3D structure of water. As you can see, the bond's angle from one OH bond to the other bond is not 180 degrees, but instead 109.5. Now, so the bond angle here on this simulation is not very accurate. It should be 104.5 degrees, but this still gives us a pretty good approximate. So that's how the number of electron groups surrounding the central atom can affect the geometry of the central atom. And as you can imagine, if a molecule were to now have multiple central atoms, then overall all of the group would be repelling each other, and that indeed would result in the 3D structure of the molecule. Now, so now let's go over some of this terminology right here, because we learn by recognizing the different types of geometry. So here in this case right here, so let me go ahead and delete the 2 lone pair of electron. There are 2 types of geometry. First one, molecular geometry. What is the molecular geometry? The molecular geometry is basically the orientation of all of the atom. because in reality we do not see the electrons. We can't see electron. All we see when we look at this molecule would be seeing these 3 atoms right here. And how are these atoms right here spread? What is the overall shape of these 3 atoms? And in this case right here, if we were to ignore this bond and just look at this 3 atoms, we can see that this molecule right here are very flat or linear with respect to each other. So therefore, we call this the linear molecular geometry. Now, the electron geometry, it basically shows the orientation of the electron group. Here in this case, we have one electron group, here is another, and in this case right here, they also spread out in 180 degrees. And in this case, it also is linear as well, so we call that linear as well. If we were to now add in another electron group, and now try to take a look at the molecular geometry, again, the molecular geometry is basically the shape of how this atom distributed with respect to each other. So overall, what is the shape of the molecule? And here in this case, we see that the molecule will be flat and it's split out in a triangle. So therefore, we call this trigonoplanar. And here in this case right here, if we were to be looking at the electron geometry, so basically refer to this electron group, and this electron group. And in this case, they also spread out in linear as well, and also trigonoplanar. So if we were to now go ahead and add in another bond, so in this case, now the central atom have 4 electron groups. So if we were to now ignore this bond right here and simply just look at the distribution of all of this atom right here, then we will then see a molecule overall will now have some sort of 3-dimensional shape to it, and it adopt a shape of something that we would call a tetrahedron. And therefore, this orientation of atom right here, 4 atoms surround this central atom, we call this tetrahedron. And if we were to now look at the number, the distribution of electrons group, and in this case look at its electron geometry, we would then see the 4 electron group would also spread out this way as well, so we also call that tetrahedron. Now, let's see what happened if we were to now delete one of this bond and now replacing it with one of the lone pair of electron. So do you see how that the names of the geometry changed down here? So the molecular geometry is now trigonal pyramid, but the electron geometry remained to be tetrahedron. So what's going on? So here in this case right here, if we were to be looking at the electron geometry, we will find this molecule and its central atom has 4 electron groups. 1, 2, 3, 4. They repel each other. So the orientations of the geometry of all of these 4 electron group right here will then be still tetrahedron. Thus, its electron geometry remain to be tetrahedron. But if we were to now look at the molecular geometry, again, when we look at this molecule, we do not see the electron. All we see is the position of these 4 atoms right here and how they connected together. So overall, we always see would be this atom, this atom, this atom, and this atom. And here in this case right here, it looked to be like a pyramid and split out in a triangle manner. So therefore, we call this trigonal pyramid or trigonal pyramidal. Good. So hopefully you can go to this web link right here, and hopefully that you can pause this so you can take a look at this link, and it has many, so you can also play around with this simulation as well. And if this is also a good time for me to introduce you to this link right here and some of the resources that may be available online that can be helpful for you. So here in this case, this is the website. And in addition to having chemistry simulations, there's also many other simulations as well. So if you were to now click on chemistry, you will find many other simulations covering other topics here in chemistry. And in a little bit, we will go back to play around with this simulation to also, and we'll be looking at using the molecular polarity simulation. So here it is. Here, this is simulation that go over molecular polarity. So now let's go back to our notes so we can write something. So here in this case right here, let's go over this to make sure all of you understand how to use this table. So this is a very nice handy table that summarizes the names of all of the different geometry. So here in this case, I want to be clear, all of this name right here correspond to the molecular geometry. So how do we determine the molecular geometry and the electron geometry? So let's go over this table. First, the steric number here. This is the number of electron group surrounding the central atom. So we want to be looking at how many electron group does the central atom have. Now, a bond is considered to be one electron group. A lone pair of electrons is another electron group as well. A double bond is also one electron group. So a double bond is one electron group. It is a bigger electron group than a single bond. However, it is still counted as one electron group. So to be able to determine the electron geometry is really easy. We simply basically look at this first column right here. And this would then be for the electron geometry. So if the central atom were to have two electron groups, it does not matter what kind of electron group it is, whether it is a bonds or a lone pair of electrons. If overall there are two electron groups surrounding the central atom, its electron geometry would be linear. If there are three electron groups, the electron geometry would then be trigonoplanar. If the four electron group, tetrahedral. If there are five electron group, we call that trigonobipyramidal. And if there are six electron group, we call that octahedral. So let's write it over here. Electron groups, electron geometry. So we do not care whether it is a lone pair of electron or a bond, all counted as one electron group. If there's one electron group, if there's two electron group, if it has one electron group, it wouldn't be the central atom already. But if there's two electron group, then the electron geometry would be linear. If there are three electron group, it would then be trigonoplanar. If there are four electron groups, it will be tetrahedral. And again, an electron group here, it does not matter what types of electron group it is. A single bond, a double bond, or a triple bond, or a lone pair of electrons. All of this is simply counted as one electron group. Now, we can also go over 5 and 6 electron group as well, but here in our Chem 300 class, we simply will restrict to only 4 electron group. In Chem 400, you will learn more about 5 and 6 electron group later. So this will then be later. And for now, we need you guys to remember all of this terminology: linear, trigonoplanar, and tetrahedral. So that is for electron geometry. So how do we then determine the molecular geometry? Now, the molecular geometry is a little bit more difficult, whilst just slightly a little bit more compared to the electron geometry. So there is a distinction between what types of electron group it is. In this case right here, how many lone pair are there? So because if we were to be looking at, go back to our simulation and click on molecular shape. Go back to our simulation again. And now let's build a model. And here in this case right here, if we were to have one lone pair of electrons, in this case, and now let's click on this, so it gives us the name of this different geometry. So in this case right here, if there are 3 electron groups, and one of which is a lone pair of electron, it's now a trigonal planar. If they're 4 electron group, and now in this case right here, 2 of them are lone pair of electron, then now the molecular geometry, this is now bent. Now the electron geometry would still be tetrahedral because overall there are 4 electron groups. But because 2 of these 4 electron group are lone pair of electron, so all we see right now would be these 3 atoms, and in this case it seems to be bent a little bit around the central atom. Thus we call this bent. If we were to now have a, let's say we have take out at 3 and another one, and here in this case right here there are 5 electron O group all together, but the shape of the molecule now go back to being linear. Here this case linear. So as you can see, it doesn't matter how many lone pair of electrons that we have surrounding the central atom. Therefore, and that would then give rise to different types of molecular geometry. So it's very important that we now ask ourselves, of all of the electron group that we have, how many of them are lone pair and how many of them are the bond. So going back to this diagram previously, so here in this case right here, anytime, so this whole entire table right here would correspond to the possible name of the different types of molecular geometry that we would find. So here in this case right here, if we would have 2 electron groups, and of the 2 electron group, none of them is a lone pair, so 0 lone pair, then the name of the molecular geometry would be linear. If we were to have 3 electron groups, and of the 3 electron group, there are 0 lone pair of electron, we will then land in this box right here. And the names of that molecular geometry would now be trigonal planar. If we were to now have 3 electron groups still, and now one of it is a lone pair of electron, we would now end up in this box. And the name of that geometry would then be called bent or angular. And here in this case right here, so we also have this diagram right here to show you how to draw what is the 3D shape of this molecule. And if we were to have 4 electron groups, and of the 4 electron group, none of it is a lone pair, so 0 lone pair, we would then be landing in this box right here, and the name of that molecular geometry would be tetrahedral, which would be the same things as the name of its electron geometry. But if we were to now have 1 lone pair of electron, so if one of the 4 electron group is a lone pair, then now we will be landing in this box right here, and the name of this molecular geometry would be trigonal pyramid. And this is a diagram to show us how to draw it. And if 2 out of the 4 electron groups are lone pair of electron, then now the names of the molecular geometry would be called bent or angular. And in this case, this is how we would draw the 3D shape of the molecule. And this diagram right here would also give us an approximate bond angle. Let's now try some of this example over here. So here in this case right here, let's now try to figure out what is the electrons and the molecular geometry of some of this example. So here are some of the molecule. Now first, we have to be able to draw the Lewis structure of it. So here in this case, the Lewis structure of this molecule, if you were to draw it out, it will be as follows. So what will be the electron geometry? Again, anytime we ask you for electron or molecular geometry, you need to be looking at the central atom. not the terminal atom, but the central atom. So here in this case right here, the central atom is the carbon. And right now, the carbon atom have 4 electron group on it. So now let's first determine its electron geometry. Let's say Eg stands for electron geometry. Because the carbon have 4 bonds group and 4 electron group total surrounding it, its electron geometry would then be tetrahedral. And now the molecular geometry. Of these 4 electron group, none of them are a lone pair of electron and all of them are bonds. So we have 0 lone pair of electron. Thus, the names of the molecular geometry would also be tetrahedral as well. Good. And now moving on to this our next example. NH3. The Lewis structure of NH3 is as follows. And I should hope you are now able to draw Lewis structure. So here in this case right here, what would be the electron geometry? To figure it out, we need to ask ourselves this question. How many electron groups surrounding the central atom do we have? And we don't have to distinguish between bond pair or lone pair. So here in this case, this central nitrogen atom have 1 electron group, 2 electron group, 3 and 4 electron group. And because it has 4 electron groups surrounding it, its electron geometry would be tetrahedral. And now, moving on to the molecular geometry. Of the 4 electron group, one of it is a lone pair of electron. So if we were to go back to our table, 4 electron group, and one of it is a lone pair of electron, we will be having trigonal pyramid or trigonal pyramidal. So here now we know this is trigonal pyramid. And moving on to the next example would BF3. Here in this case, the Lewis structure of BF3 is as follows. Now, boron is quite a special element. It does not have an octet of electron. However, it is stable. So that is Lewis structure right there. And if we were to now determine its electron geometry surrounding the boron right now, how many total number of electron groups do we have? We will then see 1, 2, and 3. So overall, there are 3 electron groups. So thus, its electron geometry would be trigonal planar. And now let's determine its molecular geometry. Of the 3 electron group, none of it is a lone pair. So therefore, we would also have trigonal planar as well. And now moving on to example of water. Water. This is the Lewis structure of water. And you can see that here in this case right here, water have 4 total electron groups surrounding it. 1, 2, 3, 4. So therefore, because there are 4 electron groups all together, the electron geometry would be tetrahedral. And the molecular geometry, in this case of the 4 electron group, 2 of them are bond pair and 2 of them are lone pair. So we have 2 lone pair of electrons. Thus, the molecular geometry would then be bent or angular. Now, this is why very important that we draw Lewis structure correctly and do not miss out on the lone pair of electron. The lone pair of electron on the central atom is very important because it dictates the types of geometry that we will see later. And geometry of the molecule again is very important because it affects the function of the molecule as well as its many other physical properties. So, molecules have a three-dimensional shape to them. How do we draw them? Certainly, it is not easy because we are trying to draw something that is 3-dimensional onto a piece of paper which is only 2-dimensional. So it is not easy. Thus, this is how we would approach this right here. And this is why it's very important that we go back and look at the diagram that's been shown in all of this. So here in this case, if we were to now go back to our simulation, we will see as follows. So let's build this molecule. So I'm gonna delete. So we'll try to create the molecule that we have seen before, and now 4 electron groups surrounding it. So this is exactly the shape of the molecule that we have seen. So in this case, the example is CCl4. So the carbon is the central atom, and we have 4 chlorine surrounding this central carbon. And now if we were to go back, we can see this molecule right here is 3-dimensional. So how do we draw this 3-dimensional molecule right here onto a piece of paper? So the approach is as follows. First, rotate this molecule right here around and find as many bonds or atoms that you believe to be flat with respect to each other. And here in this case right here, if we were to look from this view, then we would then see that this atom, and this atom are flat with respect to each other. And if we were to be looking around this view, we will also find that this atom, and this atom, and these 2 bonds right here are flat with respect to each other as well. So first, find the orientation that will have the most bond or atom that are flat with respect to each other, and we can set that to be the plane of the molecule. And here in this case, let's assume we focus on these 3 atoms right here. These are flat with respect to each other. So now we want to set this to be the plane of the molecule. What you will then do is then rotate this plane right here, so that way it lined up with the plane of the paper. So we can draw that directly onto our paper. So here in this case, we now see this atom, and this atom right here, and these 2 bonds, it will be the plane of the molecule. And now, with respect to this purple atom in the middle, we have this white ball right here. This group, it is actually pointed out of the plane toward us. And the other atom in the back, it actually pointed in the back and also down away from us as well. So that's how it actually look like. Now, bonds on the plane are very easy to draw. And when we try to draw them structure, the structure of this molecule, we will be making this bond right here. We will draw this as flat bond. And to show how this bond right here, these 2 bonds are pointing in and out, we'll be using dash and wedge bond. So if we were to now go back to the structure, that's exactly what it would look like. So anytime we draw 3D structure, and if we were to see this types of bond right here, this basically means that these 3 atoms, and these 2 bonds are on the plane of the molecule. On the plane of the paper. And these are 2 other groups, this chlorine and this chlorine. This one right here, it is pointed out. And to show this is pointed out, we use this bond right here. And this is the bond that we call to be a wedge bond. A wedge bond means that it pointed out of the plane. And the other bond in the back is then called a dash bond, because it is being dashed. And now a dash bond means it pointing into the plane. So once we have all of this understood already, we will be able to see how and draw what does the 3D shape of this molecule look like. Good. So now note a few things that may have mentioned before already. When it comes down to the electron group, 2 or 3 electron pair in a multiple bond behave similarly as a single electron pair when it comes down to the geometry. This basically means that double bond and triple bond behave similarly as single bond when it comes down to the molecular geometry. For an example, if we were to have VSEPR, in this case right here, the central atom have 2 electron groups and both of them are bonds. So therefore it would be linear. And if we were to now look at another example with CO2, in this case right here, the central carbon have 2 electron groups on it, and they are double bond. And again, it is counted as 2 electron groups. So therefore, the geometry would be linear as well. And now moving on to this example right here, this carbon right here has 2 electron groups on it. There is a single bond and a triple bond, but both of this are discounted at 1 electron group each. So therefore, its geometry would also be linear as well. And if we were to go to another example down here, so the central atom have 3 electron groups on it. So we have a double bond and 2 single bonds, but there are 3 electron groups altogether. So the electron geometry and the molecular geometry would then be trigonal planar. And here, this is also trigonal planar as well. So in conclusion, it is the number of regions of electron density or the number of electron groups surrounding the central atom that determine the molecular geometry and the electron geometry of the molecule. A lone pair of electrons, a single bond, a double bond, and a triple bond are all considered as 1 electron density group. However, the lone pair of electrons interact strongly compared to the bond pair of electrons. And the reason why this happens is because the lone pair of electrons consists of 2 atoms, 2 electrons in the one orbital. So technically speaking, the orbital is a little bit bigger, and therefore they repel each other a little bit more. But then this is the one concept that we will discuss further in more detail in Chem 400.